Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to welcome GIUSEPPE de NITTIS, who used to be from southern Italy, now he's from Southern America, all the way from Santiago de Chile. And today he will tell us about the magnetic spectral triple open question and applications. The Zoom is yours, the floor is yours, take it away.
Thank you very much, Piero. Thank you very much for the invitation here in Warsaw and this very important international series of talks. And I want also to thank the guys here in the room and the people online. First of all, let me say that my talk will be as pedagogical as I can. I want to stay in a very low ground. I would like also to give some physical motivation. I know that this is essentially a mathematical seminar, but the inspiration to this result is from physics. I will explain you, give you a series of results that I obtained in the last year with several collaborators, Fabian Del Monte, Massimo Moscolari, Maximiliano Sandoval. But I have to say, and this is very important, I want to remark that the origin of this research dates back to 2012, if I'm not wrong, when Jean Belissard, which is online, suggested me to rethink at the problem of the quantum Hall effect, trying to change the basic zero operator. Then I remember that we met once in Sendai in Japan, and there in this place we start talking and having the first idea how to construct this object. And then finally, let me say that the main inspiration to this work indeed is an idea by John. Okay, just this is a short content of what I want to say. I would like to start with a review of the quantum Hall effect and Belissard. Then the magnetic spectral triple that we imagine during this time for the case of pure magnetic operator without potential. Then I would like to say something about perturbation by potential, and I would like to end just with open problem, which essentially is the collection of things that I would like to do, but I'm not able to do, and some possible application. Okay, first of all, quantum Hall effect. Just let me start with a bit of history because it's interesting. You know, the idea of the Hall effect started in 1879 when this guy, Hall, just playing with Maxwell equation, come with this result that in presence of a perpendicular magnetic field and a potential which drifts some current, the Maxwell equation just predict a potential which is transversal, a transversal flux current. In 1918, von Klitzky started measuring this effect in the limit of a very small temperature, ideally the 0 Kelvin. Why? Because this is the region in which quantum mechanics, in some sense, dominate classical mechanics. Indeed, he discovered what now we call the quantum Hall effect, which is the quantization of this transverse current. Then this was surprising because, you know, it was not clear why this current should be quantized, but just 1-2 years later comes the first theoretical explanation by Laughlin and Toles and all in a very seminal paper. And just since from the beginning, the interpretation of this result was based on topology. This is more or less the year of the birth of the term topological quantum number. And in the 1994, this is the year in which Belissard published his seminal paper on his business, which is the noncommutative geometry of the quantum Hall effect. Even though this is the date in which the paper was published, but studies was already done during the 80s. let me just finish with the last comment where, quantum effective and quantum system are relevant because it was in some sense the prototypes of a large class of system, which today are called topological insulators. Okay, just the quantum system was the first, probably for a long time, the more interesting guys in a zoo of different systems that today we call topological insulator. And for this kind of guy today, we have table of classification, different classification schemes, and huge industries. But everything indeed starts with the quantum effect.
Correct me if I'm wrong, but von Klitzing got a Nobel Prize for his work.
Yes.
Right?
Yeah. Correct.
2016, am I right? Something like that.
This I don't remember, but I remember he was in ICTP in Trieste.
Yeah, I'm not sure. I think that it's correct, the year, but this was more or less. Yeah, just a picture of a quantum Hall system. I think everybody has seen this before, but here we have a material which is ideally two-dimensional. And the quantum Hall effect is really a two-dimensional effect. We have a perpendicular magnetic field B. We have something which is forcing a current in the horizontal direction. And because of that, we have a transversal differential potential. This is called the Hall potential. And that's everything I would like to stress about this slide. And this is what happened in the experiment. This also is a very common picture. You can see here. Here, indeed, what is plotted is not the conductivity, but the resistivity, which goes as 1/n, this constant, which is called the von Klitzing constant, which is just given in terms of the Planck constant and the charge of the electron. And you can see that you have these plateaux, which are very quantized. But these plateaux indeed are interesting because the quantization just fixes the number, but it's important also to explain why this plateau exists. And indeed, the explanation of the plateau is due essentially because of the impurity. In some sense, if you want to see this picture, we have to stay in a system which is not completely clean. We need some impurity because we need to force what is called the Anderson localization. Because of the impurity, there are certain states of the system which localized and which fill the gap between two, let me say, Landau level. You can interpret this peak as the Landau level of the system. These allow essentially the particle, the density of states to be, in some sense, continuous, to change without changing the conductivity. The conductivity just jumps when I jump a Landau level. Then, an explanation of the picture that I showed you before, in which I have the quantization of the resistivity or the conductivity is equivalent because one is the inverse of the other. And the plateau at the same time need to consider systems which are magnetic system and at the same time disorder system. Then we know after the, essentially after the work by Torres and the co-worker, that the quantization can be explained in terms of Chern number associated with certain spectral projection of the Landau level. But for what I just tried to explain you and convince you, if you want also to explain the plateau, we need to include disorder, randomness. And this is done in the mathematical formulation, switching from one operator to a family of covariant operator, which are indeed indexed by different configuration of the disorder, of the potential, if you want. Then, if we want to explain at the same time quantization and plateau, we need a theory in which we can consider covariant family of operator, then a family, a theory of operator than a theory in which we are working with algebra operator, and then sometimes we need to reconstruct a topological quantity like chain number, chain characters, maybe it's more correct. And this setting is exactly the non-commutative geometry of the cone. This was the main insight by the work by Jacques, which is here. And in 1994, it appears this paper in which all these ideas are summarized. Okay, the use of non-commutative geometry to explain at the same times quantization and Plateau. Now, just I know that this is a seminar in non-commutative geometry, but I repeat, the idea was to be pedagogical as I can. Then just let me recall what is a spectral triple. And I took this definition from Kohn book. A spectral triple or chi cycle is given by an Hilbert space, an operator D. I have an algebra with involution. I can represent the algebra on the Hilbert space H. Okay, well, I assume that it's already represented. And this operator D, which we will call it the Dirac operator, is an operator with compact resolvent. And when I compute the commutator of D with the element of the algebra, this commutator should be bounded. Okay, these are the main ingredients of a spectral triple a la Kohn. And I stress the fact that I would like to insist on the compactness of the resolvent. Why it's important, the spectral triple? Let me give just some geometrical interpretation. There is this reconstruction theorem by Kohn, but many other authors worked to a complete and definitive proof of this theorem, which was much more longer than the initial sketch of the proof given by Alain. But it's interesting. Essentially, this theorem said the following: if I have a spectral triple, and if the star algebra is a commutative, and if it meets certain number of conditions that I don't want to stress here, then there exists a compact-oriented smooth manifold such that A is the algebra of the smooth function X. In some sense, a spectral triple is giving us a generalization of a smooth Riemannian manifold in a setting in which my space is not a space of point, is a non-commutative space. Okay, then in some sense, spectral triple, in some sense, in all the sense, spectral triple are non-commutative Riemannian geometry.
Maybe it's worthwhile to emphasize that the main difficulty was to distinguish between omnifolds and smooth.
Thank you for
this is what we're struggling with, and I also remember Alain saying that this was so difficult that he would have nightmares where they were not mistaking his proof, which for a person like Alain is kind of amazing. So if it was difficult for him, it was really, really difficult.
No, you know, indeed, this result is a difficult result. At this level, would like just to give a justification why we can claim today with a certain liberty, freedom, that a spectral triple is indeed giving us a notion of Riemannian geometry in non-commutative sense. I will never use nothing of this method, but this is just for clarity. Now, let me go a bit in the content of Jean's work, because then I would like to explain what we did differently. Well, first of all, I would like to construct a spectral triple to treat quantum Hall effect. And let me start with the algebra. The algebra is constructed in this way. I need essentially an ergodic dynamical system with a Z2 action and an ergodic measure P. Omega is compacted out, okay? And then what I do is the following. I need two unitary operators which commute up to a phase. This phase is an incarnation of the magnetic field. If you want, this look like such a non-commutative torus, but I need more. I need the function, the continuous function of this sister algebra C omega. And I need also to understand how this function and this unitary interact. In some sense, what I'm saying here is that when I commute f with the unitary, the JF unitary, I'm just translating the function in the direction J. Why? Because, you know, I'm saying that in this omega, in the space omega, I have an action Z2, then it makes sense to speak about translation. Z2 is acting on omega by translation in two directions.
So tau is the action of Z2 on omega. Tau is the action.
Tau is the action, because of that, this is an ergodic dynamical system. Tau is the action of the Z2 action over omega.
And what is E?
Is an ergodic measure with respect to the action.
The ergodic measure.
Okay. Omega admit measures. P is an ergodic measure in some sense is an invariant measure and is an invariant measure, is an ergodic. Okay, once I have this rule, I know how to multiply this element. I can cook a sister algebra. Okay, this sister algebra can be defined in several different ways. It can be closed between. It can be closed in principle in different norms, but because of the abelianity of Z2, essentially all the sister norms are equivalent. Then there is a unique sister algebra which makes these properties, but I prefer to give directly a complete representation because it's the one that is used.
Oh, sorry, once again, this B is what? It's invariant measure?
B is an ergodic measure.
Ergodic measure. So what does it mean, e to the power IB?
Okay.
No, B is a number. B is just a number. It's the magnetic field or the magnetic flux.
So it is fixed once and for all, yes?
B is fixed.
Okay, so P is an ergodic
Yes,
measure.
this one.
Okay.
This,
P, not B. Okay.
It's okay?
Yeah.
Yes, thank you.
Okay, then just a complete representation of my algebra. First of all, the two unitaries are nothing more than the magnetic translation on L2 of Z2. I'm translating in the two coordinates and I am adding a phase, which is the magnetic phase.
So it smells non-commutative torus.
Yes, it is non-commutative torus modulo the fact that I have something more, I have the presence of the disorder. And okay, maybe just because
You might shrink it a little bit. I don't know how to. Yeah. No.
Okay.
Just wait a second. Maybe that one. I'm always to the page. Maybe this one. Yes. Okay. I hope now it's fine. Yes.
In the formula for U2, sorry.
No, I don't know what it is.
Oh, somehow the screen disappeared.
Yes. Okay. It crashed. This is a quantum screen effect.
I did nothing. I'm not responsible.
Conductivity.
Okay, so in this formula for U2, you have some strange comma. I presume that.
No, it's a mistake. Sorry.
Yeah,
Just
okay, that's the
this
type.
one is just a mistake. Is
Okay.
should not be there.
Okay.
There should not be there.
There's one type of correct.
Now, how represent my continuous function of omega? In this way, you see, I can fix a point of omega, and you know, I have tau, which is my action of omega, and then I can move the point of omega according to the point of Z2. Then I can define an operator, which is the multiplication operator, what I call the MF omega, such that when apply this to the vector C in L2 of Z2, and then what I obtain is psi evaluated in N, and F evaluated in the translation of omega with respect minus. Okay, this gives a representation of my algebra C omega on my Hilbert space L2 of Z2, and you can prove that these relations are indeed satisfied.
I have a question.
Oh, sorry, this looks like a cross product, is it right? Sorry. Mhm.
Just no, my first.
So my question is, could we interpret these operators U1 and U2 as some parallel transport in a gauge field corresponding to the B?
These are nothing. This is okay now. The answer is yes, when I will interpret this in the continuous, where essentially I will have the magnetic moment. These are nothing more than the exponential of the magnetic moment. Here I'm in a discrete space. It's difficult to have this geometric picture. Okay? But indeed, this is the discretization of what we have in mind.
Yeah, it's on the lattice. It's a
Yeah, I mean, now I'm on the
it's
lattice.
on the lattice.
Now I'm on the lattice. I'm on the lattice because on the lattice is simple.
Yeah, so if you go around a small square,
Well, from this relation, you just will obtain a EB, the identity operator, which measures the magnetic flux around the unit cell.
yeah, but I'm not talking not about this abstract relation, but I'm talking about these translations.
But you see, this translation realizes this one. The
Yes, of course.
condition that
Yeah, yeah, yeah.
is indeed
But this realization reminds me I'm going around the square this way or that way, okay? And
exactly. No, you're right. This is when this you are computing the circulation of the holonomy of your vector potential, but because I'm in the discrete, I don't really have this differential notion.
So
But it's the discrete version of what you are
so this number, in fact, is an integral of these two forms over this square.
over the age of the lattice. Okay.
Okay,
No, over this square.
Okay.
Adam, now.
Yes, sorry. So is it the same as a cross product? Is that-
It is a complete representation of the cross product.
Okay.
I think that I will mention this, but well, you know, I prefer to give the indeed to be. The prescription here is really the construction of the cross product. This is a concrete representation, realization, because of the one that I want to use. Now, what about because I want to construct the spectral tripole. I'm saying nothing new. This is really everything Jean did in his paper. I'm just repeating the construction that is in the paper. The Hilbert space for the construction of spectral tripole is just tensoring L2 of Z2 with this C2 fiber. I need indeed this sort of spinorial degrees of freedom because I want to put there a Dirac operator. Understand this? And I will represent my algebra just diagonal on this grading. Okay, I take an operator A and I have it is diagonal representation. I'm fixing omega because omega is my reference point in this big omega, which is a space of disorder, which allows me to construct this multiplication operator, which is a spectral tripole. You know, in Z2, I have two nice operators, which are position operator, and I can construct this Dirac operator, you know, mixing the position operator on the lattice with the first two Pauli matrices. What it happened is this guy. This guy is a guy with a compact resonance. Why it has compact resonance? Because on the lattice, the position operator are discretized on the sides of the lattice. Okay, and so because of that, these are discrete spectrum. If I compute the resonance, it's just compact. Okay, then let me stress this point that will be important for my talk. The fact that in this approach, the Dirac operator are compact resonant is really because the nature of the Hilbert space in which I'm working is this. Well, I think that I don't have to insist on this point. Once I have the Dirac operator, I can construct the Dirac phase, which is just the phase associated with the Dirac operator. Well, a priori this operator, well, you know, this definition should be taken with the fact that I have to be sure that I can invert the modulus of the Dirac operator, but you know, you need just a regularization because you have to avoid the ground states, but you know, it's a technicality, that's not a problem.
I have again a question about the physical meaning of this Dirac operator. So usual Dirac operators related to differentiation. Now you are taking, instead of partial derivatives, you have position operators like coordinates. So does it mean that now we are in the dual space of momenta?
Yeah, I mean the discrete, I don't moment.
No, there's a discrete action of this Z2. It's a lattice. So it looks like we are speaking now about the lattice in the space of momenta.
I don't know, in some sense, you know, because I'm an L2 of Z2, I have only a notion of translation. I don't have the infinitesimal generator of the translation which give me the momenta. But what I have for sure are the position operator.
So sorry, this position operator is just multiplication by what? By the coordinate?
By the index of the
in Z.
lattice.
Yes, in Z square.
Yeah.
So those are unbounded, yes?
Are unbounded.
Unbounded, okay.
But they are completely diagonalized on the basis of L2 of Z2.
So it is like Thomas was saying, something done in the dual picture, I presume, yes? Since usually Dirac is defined in terms of differentiation, and you don't have differentiation.
But you know, you can define the Dirac in terms of differentiation also in the continuous, but by a Fourier transform, you can replace differentiation with multiplication by position.
Yeah, but
Is it just
Yes, but taking Fourier transform is going to the momentum space, yes?
Let me take this point of view here. I'm deciding to use the position operator and don't take this Fourier transform which send me back to the momentum because I don't have momentum. I have just translation. Okay?
Yeah. So I think that that was exactly what Tomasz had in mind. Am I right?
yes.
Okay, well, I'm not against you taking this point of view. If you want, you can think that I'm working in this in the dual picture with respect to the momentum. But what I'm saying, this is an operator. Just I need to be sure that it's doing the right things that a Dirac operator has to do in a spectral triangle. And then just let me see which are the consequences of that. There are some interesting results obtained by Melissa with this construction. This is the first interesting result that I want to stress. There is a formula which is relating two types of trace. In this first formula, I have the Dixmuir trace. I'm taking the inverse power of the modulus of my Dirac operator, which is just what I showed you in the previous slide. I have powers minus, in my case, I'm interested in the case -2. This computation work also for different D, but just fix D equal to, and just is, oh, perfect, it's enough. And on the other side, what I have another type of trace. I would like, first of all, to fix on this trace. This is what is called the trace per unit volume, which is nothing more in physics than the computation of thermodynamics quantities. How it works? I take my element of the algebra represented in my representation omega, I'm fixing omega for the moment. I project my operator with the characteristic function of a set lambda, finite set lambda in Z2. You can prove now that this guy is trace class. You can compute the trace and you normalize or you divide the trace by the volume of my cell lambda. And then I take the limit when lambda goes to Z2 this limit should be understood in the sense that these lambda are a Follner sequence, but just to understand, I just can take square of length L with L, which goes to 2, okay? And then, because I have an omega, I just make an average in omega, because omega belongs to this space, big omega, in which I have an ergodic measure P, and I can make an average. It's not only ergodic, it's ergodic and normalized, but I'm just making the average on the space of configuration. This gives me a trace. What is a Dirichlet trace? The Dirichlet trace is a way to compute the trace for operators for compact operators which are not of trace class. Let me say differently. When I have an operator which is a trace class, both trace class operator, the trace of this operator is just the sum of the eigenvalues. It means that the eigenvalues should decay fast enough. What happened, for instance, for positive compact operator with eigenvalue which decay like 1/n? This sum does not converge, but I can renormalize this sum with the log of n, and then to compute the limit. This gives me the Dirichlet trace. Now, this limit is not a unique limit, is a scale invariant generalized limit. I can choose one of them. There is some technicalities indeed in the definition of this trace, but this is the most important information that I would like just to give you to understand, to have some feeling of what it is. And now it's very interesting that from one side I have this trace per unit volume, which is giving me some thermodynamic quantity on my lattice Z2, and here another trace which is in some sense just giving this averaged sum of the eigenvalue. And even more important, there is the modulus, the inverse of the modulus of the Dirac operator, that is giving me this equality, okay? Well, the second result, this is taken indeed from the GIUSEPPE paper, is something which goes more, in some sense, this aspect is not geometric, it's more geometric aspect, but to start having some more geometric information, we have this formula that was called the first cone formula in the Belisard paper, and essentially is giving this. Again, I prefer to have the complete slide. At the level of my algebra, I can define certain derivatives, which are just the commutator of the element of my algebra with respect to the position of it. Okay? And at the level of where the spectral triple is defined in this space, which has is tensored by C2, I can define a notion of differentiation, take an element of my algebra, I can represent it, and I can compute the commutator with the Dirac phase. Okay, this is D times the modulus of D dimensional. Okay, I have these two elements, a gradient in my original algebra and a differential in this algebra in which, a larger algebra in which I define my spectral. Now, from one side, I can compute the trace per unit volume here. This simple is again the trace per unit volume of the modulus square of the gradient in my original algebra.
So sorry, this gradient is defined for A or for A omega?
Same question.
For A omega, it's but I think that in this formula is not put at the A because the trace per unit volume has an average on omega. Okay. And on the other side, I can compute the Dirichlet trace of the modulus square of the differential, and the two guys are linked. There is finally a third formula. Again, just I prefer to have all the information on the same slide. There is a third formula which related on the level of my algebra that I showed this three linear form, which is indeed a ecocycle. Again, I have the trace per unit volume. I'm just computing this combination of three different elements with the derivation that I showed you before. Okay. And on the other side, here I'm in this enlarged Hilbert space in which I have my spectral tripole. I can compute the trace of these elements, which are elements of it happened what should not happen. These are elements of a sort of the RAM cohomology that I will show you. Okay, these are form of order 2. And I'm tracing these with a graded trace, which take care of the graded structure of the space in which I define my spectral tripole. I compute this integral, and again, I have this equality. And this is important because, you know, this is nothing more. When I fix this guy for instance, a projection T, this is nothing more than the non-commutative version of the Chern character of the projection. Okay, indeed, is this formula that gives me the quantization of this guy, which indeed, with another deep result in physics, can be interpreted as the Chern conductivity. I will not enter much on this business, but essentially is this formula which is explaining the quantization of the quantum Hall effect, because this guy is quantized because topological reason. This guy can be re-expressed as the Kubo formula for the conductivity. Well, these are essentially is a summary of the result that there are in the paper, in the Jean paper. And as let me stress another important aspect. Really is important the fact that D has a compact resolvent, this type of result, and the fact that the D has a compact resolvent also allow a very strong computational algorithm to compute, for instance, this Chern class, just because I can approximate my Z2 with a big but finite piece of lattice. I can write this as a matrices, may put this in a computer and make that computer compute this number. You know, in this book, Emil Prodan give a complete program how to compute with this discretization method, this topological number. And also in a series of work by Hermes Baldes, Terry Loring, using essentially the discreteness of this Dirac operator, there are possibility of calculation of these topological invariant, which are indeed in the K theory, in terms of operator defined in a finite value.
And the author of the book is coming to our workshop next week.
I know. When
I don't remember, it's on the page, but 52 people I memorize the dates.
Now let me now enter in the new part in some sense.
So you begin your talk.
Okay. Let me say that up to now, I just tried to summarize the important point of the Jan work. Now, what I would like to do is just to add probably an epsilon to what he did. But the main difference now that now I really want to work in the continuous and not in the discrete. Okay. Now, the main point is it's possible to repeat what Jean did essentially in the discrete, in the continuous case. And the most important point, it's possible to construct a spectral tripole with the properties that the Dirac operator, which is the main object of this spectral tripole, should have compact resolvent. Okay? And of course, it has to do the right thing. Now, let me fix some notation. When I work with in the continuous, I can write my magnetic system. There are essentially two main numbers which comes from the physics constant. One is the magnetic length, and the second is the magnetic area. I can use this guy to write this family of 4 operators, K1 and K2, G1 and G2.
Sorry, what is M?
M is the mass of the electron of your charged particle, and Q is the charge of your particle.
Yes, yes.
Okay. Thank you for the question. You know, I'm using this scaling. It's not trivial, you know, because in this way, in this moment, I'm in physical unit. X1, X2 are position, then are the dimension of length. I'm dividing this by length. Then in some sense, my constant K1 and K2, G1, not my constant, my operator, K1, K2, G1, G2 are dimensionless. Now, then we will start doing mathematics and we can forget about this by the dimension, but I will still keep L here because look, what it happens when B goes to 0? When B goes to 0, L explodes. Then in some sense, the limit of zero magnetic field will be a singular limit for everything I will say, okay? Then indeed, all the result that I will present you just are result valid at no zero magnetic field. This is, I would like just to stress this point. Okay. Easy check.
Sorry, but it is even worse, because if LB explodes, then LB also appearing as a factor in the first summand tend to 0. So it will not be.
Yeah, but it's a singular limit. In some sense, I'm saying nothing more than the fact that if you take the Landau Hamiltonian, this is a physical fact that, and you put that the magnetic field going to 0, you don't obtain the Laplacian. Okay, in some sense, it's a singular limit. And this is a way.
I meant that you have 2 phenomena here.
Yeah.
Singularity and degeneration. Okay. Both.
Nevertheless, this family of operator make this computation relation. Just computation, it's nothing difficult. The Landau Hamiltonian is generated, can be written in terms of just 2 of these variables, K1 and K2. Okay? And indeed, the G operator commute with Hamiltonian, then give me the possibility to write symmetry of my Landau Hamiltonian. Just a reminder, because I will use this extensively in my talk, the Landau Hamiltonian, this one, the Landau Hamiltonian is diagonalized on this base of eigenvectors, which are given in terms of the Laguerre function. You know, I have the Laguerre polynomial, some polynomial here, and I have the Gaussian, the ground states of my Landau Hamiltonian.
I have a question. In this eigenvalue equation, you have this multiplicity n+1/2, suggesting that this must have something to do with oscillator, harmonic oscillator, quantum harmonic oscillator.
Indeed.
Yeah. But is this Hamiltonian?
You know, we will see this in some next slide, but in some sense, the Landau Hamiltonian is just half of the harmonic oscillator in dimension 2. Okay. Remember that we are in dimension 2, we are in R2.
Yes.
In some sense, the Landau Hamiltonian is just half of the harmonic oscillator.
Okay.
Okay.
And also, Thomas, remember that the commutation relation between K1 and K2 is exactly as for annihilation operator.
Annihilators and creators.
Exactly, but we have still G1 and G2 that in this moment are just making this symmetry with the Landau Hamiltonian. Because of that, I have this M. You see, any Landau level, any level indexed by n has an infinite degeneration because of this M, and this is the effect of this symmetry. I have to take care of this symmetry, of this degeneracy in some way. And I will do this exactly reconstructing the full harmonic symmetry. Because G1 and G2 are symmetry of the Landau Hamiltonian, I can construct this unitary operator. I can just exponentiate these guys. And these guys just realize the magnetic translation. Okay, it's just the computation. Just I would like to condense this phase factor with this notation. And this provide a magnetic two cycle, a magnetic group two cycle. It's a group two cycle in all the good sets. Now, I want to do that. And then I would like to express why I prefer to do that. I want to construct an algebra which contain my relevant operator, magnetic operator. And I do that, I take this magnetic translation, and I would like to consider, well, I create the C-star algebra generated by this magnetic translation, and I declare that the algebra of interest, in which I'm interested, is the algebra of all the operator, bounded operator, and L2 over R2, which commute with this magnetic translation. It's a good definition because I know that my Landau Hamiltonian is commuting with this magnetic translation. It means that the spectral projection of my Landau Hamiltonian are here. Okay? And then because of that, I say that this is my phenomenon. I want to work with this phenomenon. The fact that it's a phenomenon algebra is just because it's a commutator of a system.
I'm sorry, just a silly question, but I'm a little bit confused. You wrote X wedge A. So what does it mean? X and A are in R2, yes? Just ordinary vectors, yes?
Yeah, this is the wedge
Determinant, 2 by 2 determinant.
is x1 a2 minus x2 a1.
Aha, okay. Okay. Mm-hmm.
Okay, just again, I prefer to have everything here. Okay. Now, I would like to describe this phenomenon algebra in a different, which is more helpful. For that, let me define this operator that I call transition operator. You see, what this operator indeed does, fix the eigenvalue associated to this second quantum number m. This does not change m. But, you know, if n is equal to this j, then it changes this n to k. Then, in some sense, this m physically is giving information about the angular momentum of my electron. Okay, fixing the angular momentum, these operators are moving a system of energy n to system to energy j to system to energy k. And if this is not a j, just goes to zero. Okay? These are jumping operators. You can check these properties. These are just trivial once you have this definition. In particular, the Landau projection are the operator which goes from J to J, which can be constructed in this way. And because I have whole multiplication rule and the adjoint, I can construct a C-star algebra just with this jumping operator, this transition operator. And what it turned out that this C-star algebra, the envelope hormonal algebra of this C-star algebra is exactly the one that I showed you before. And
Can I ask a question about
yeah, of course.
question to Piotr? Isn't it a graph system algebra?
Which one?
This generated by gammas.
But
It's just yes, this is the C-star algebra that you associate to a graph which is the joint point.
but so what's the graph? What's the graph? 2 points?
No, the point are n. I have n. Okay, the natural number. And you know, j is just the arrow which goes from j to k. Okay, you can construct this point.
I alluding to things like Depke's algebra.
Well,
Yeah.
Yeah, there are the rules. This is a complete
Generalization of the algebra.
I don't think that is not the this algebra.
It is. It is.
But I prefer just I prefer the physical meaning. This operator at fixed angular momentum is just moving particle of energy J to particle of energy. But because of the Landau system, the energy are parameterized by n. And then I'm just really going from the Landau level J to the Landau level K. And I can go back.
Yes, it's very interesting because this gives some physical interpretation to this graph system algebra. Okay.
So you're saying that the CB is indeed the Teplis algebra.
Well, but the interesting thing is that the enveloping from normal algebra is the algebra of my magnetic operator. And there is another result. I will not present this. This is nothing more than the group sister algebra associated to R2 twisted by the cycle that I showed you before. Realize, okay, this is the regular representation of the group sister algebra over R2. Okay?
But wait, I mean, one is compact, one is unital, one is not.
No, it's not unity. There is no unity in the system.
So it's not Teplis sign, can understand.
Yeah, so it's not in the usual sense, it cannot be.
Teplis algebra is unital. I mean,
Maybe it's
But this algebra definitely
generalized in some sense.
the unit, but are not are just the Landau projection. There is no unit in this system. Well, now let me say something. Now I tell you that this is just the CB. Indeed, is just the regular representation of the group sister algebra associated to R2 and twisted with the magnetic field. Just to give you the mystery, this operator, this upsilon JK, and nothing more the regular representation of the Laguerre function. The Laguerre function that I show you, which are the one that diagonalize the Landau Hamiltonian, are indeed also element of the group sister algebra over 2, because they are a fast function. And when I represent regular representation, they give exactly this on the Laguerre basis.
So by twisted group algebra, you probably mean
There is the
magnetical cycle.
The magnetical cycle is
The magnetical cycle which was present before. Okay.
Exactly.
Okay.
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 But I don't want to go through the twist group algebra because they are really a complete representation. It's very easy. In some sense, I'm giving a discretization of the representation of twist group algebra just because these operators play an important role. I'm using this operator because, as I told you, I'm in the continuous. I lose the discreteness of the position operator, and I'm using this operator to recover a discrete structure. Essentially, this is a bit the business. Now, well, I have this operator, this upsilon JK, and I can construct a relevant Banach spaces. How I construct these spaces? Just linear combination with coefficient which will belong to LP space. I'm really interested in P = 1 and P = 2. And you have this inclusion. These S are just Schwarz type sequence when I replace this LP with fastly decaying sequences, okay? Indeed, in this case, this SB is a pre-sister algebra. It's a very strong object. What is this guy in the middle? This guy is made by multiplying operator which belong to this Banach space. This means that I'm constructing operator with sequence in L2, and I multiply two of these, and I create this guy. You can prove that this is a two-sided self-adjoint ideal in M.
Just a silly question, where is tau in this formula?
It will appear in the next slide, and there is a reason because I put it now, because indeed this ideal is the domain of a trace, tau.
You mean a torus, not a trace.
Hmm?
You mean a torus, not a trace. Look,
it says stars.
It's stars. So 2-0 for us. We found two typos.
Yeah.
Three
It's a
before,
pass.
before it was Chem.
Ah,
It was
so,
Chem.
okay, so 3-0 for us.
There was also some double E in some mark.
No.
Sorry.
That's four typos.
Well, this is a trace. I compute this trace with this. Let me give you this definition trace because it's very simple. As I told you, I take these two elements are L2 coefficient in the expansion, and then I compute L2 scalar. But the important point that this trace is equal to the trace per unit volume. There is a way to do this. Okay, now my operator A, I can expand my operator in this way, but our operator which are living in L2/2 are magnetic operator. I can compute the trace per unit volume in the way that I showed you in one of the first slides, just localizing in some finite patch of the space, computing the trace, and then in the limit when the volume of the patch goes to infinity. Then you have this equality.
So by volume, you mean area.
Area.
You know why I got confused? Because tau used to be the action, tau is a trace.
Now it's trace.
But this was the first part of the talk. Here I have no omega and then I have no action. Okay, I have this first equality. Even in this continuous setting, I can define my derivation in same way. I can compute the commutator with the element of the algebra for certain good element of the algebra. For instance, for the one which belongs to this Schwarz type space. Now, let me construct the spectral tripole. First of all, I need here the case, which I want to define my spectral tripole. In this case, with respect to the previous case, the jam case, I need to tensorize with C4, and not only with C2. Because, well, the idea is that now I have, with respect to the discrete case, I have 4 relevant operators. Not just 2. I have the K1 and the K2, which define the Landau Hamiltonian, and I have the G1 and G2 that define my magnetic translation. I would like to use these 4. And to have a good Dirac operator, I need 4x4 matrix with 4 4x4 matrices, which realize some Clifford type algebra. It's not necessary to specify which are omega 1, omega 2, omega 3, omega 4. I just need that they realize the anti-commutation relation of CL4. But then I will give you a explicit realization. Why is it? Well, because if now I compute the square of this guy, the square of this guy is diagonal plus a small correction that indeed makes me not kind of problem. And what is QB? QB is your harmonic oscillator in dimension 2. I will not write explicitly, but you know, now is complete, is again diagonalized on the Laguerre basis, which diagonalizes the Landau Hamiltonian, and the degeneracy of the energy level is not infinite, it's finite now. Okay. These guys are finite degeneracy. And because of that, you understand now the resolvent of this Dirac operator is compact. You understand that I cannot construct in the continuous just the same Dirac operator using just the x1 and x2, the 2 position operator, because this Dirac operator will never have compact resolvent. But in this way, I can hook up an operator, a Dirac operator, which has a compact resolvent. Okay. Result. You know, the first result that I obtained with one of my former students, Sandoval, Maximiliano Sandoval, was to reconstruct the trace per unit volume using the Dixmuir trace and this Dirac operator. like in the first of the results obtained by Jean in the discrete case. Here we are in continuous. Okay, and then we can prove this formula. This dB epsilon is just a regularization because there is a ground state, a zero energy level in the Dirac. Then when I compute the inverse, I need just to regularize. But the trace, indeed, the value of these guys is independent of the regularization. There is just an important point that I would like to stress. This was one of the things that I wasn't able to do. We can prove this formula only on this Banach space L1b, which is a dense space, but does not coincide with the domain of definition of the trace per unit volume. I am convinced that this formula should work on all these domains, but for technical reason, we weren't able to prove this for the full idea. Okay? We can do something in the same series. See, for the moment we renounce to the Dixmuir trace, we can also compute now this trace per unit volume as a residuous formula. What we can prove that now we can take any operator in the domain of the trace per unit volume. We can multiply with this power of the inverse of the harmonic oscillator. Okay, this is at -1 plus delta. We can prove that this is trace class and we can compute the trace. We multiply by delta and we goes to delta when delta goes to 0. This gives us again the trace per unit volume. Okay, and we have even a third formula to compute the trace per unit volume.
Sorry, could you come back to the previous slide? So this residue formula comes from the Riemann zeta regularization. It is. Okay.
Is a form.
Is a form. Okay.
But you know, there is related because you know if we want to use really this Riemann regularization, this at -1 plus delta should be put at whole. Here I'm just what you say. This harmonic oscillator is a weight, and I'm in some sense putting this delta only on the weight and not on the full operator. You know, it's related in some sense that this is the reason because this result on the Dixmuir trace, because if I can prove that this is exactly the Riemann zeta regularization, would obtain this result for all the ideal. There is a technicality.
Okay, yes.
Forbidden me to go from year to year directly, but this formula I can check on all the ideal of definition of the trace per unit volume, but it's strongly related. There is even a third way in which I can compute this trace per unit volume, and it goes in this way. You know, let me fix a shell of energy J of my harmonic oscillator, of my operator Q. It means that I can take all the eigenfunctions such that n plus m plus 1 equal J. And let me compute, now I have my operator A, and let me compute my average on this energy shell of the harmonic oscillator. I call this average WJA, okay? Now, I sum this shell averaging from 1 to n. I normalize with the log n. And then I go in the limit. Again, these give me up to a constant the trace per unit volume. And again, this formula works in all the ideal of definition of the trace per unit volume. Okay. Then there are several ways in which we can recompute this trace per unit volume in the continuous using a discretization which is given by the eigenvectors of my Landau Hamiltonian. Okay, you know, this formula can be useful for numerical computation because you just decide where you want to truncate your approximation and give an approximation of your operating volume. To be honest, and I have also to admit a second things that we didn't yet is to compute how fast this guy converge. We have no estimates of the other. Okay, then in some sense can be useful, but could be even more useful having an estimates of the velocity of the convergence. Okay,
Sorry, so by integration, you mean depending on capital L2? Where's other?
but this is the scalar product in L2.
Yeah, so then,
But these are very
so the only meaning of integration is now the norm of L2 here, okay.
with respect to this very specific function. These are the Laguerre function. So these
Yeah.
are a very specific function. I take my Laguerre function, which are in Mathematica. I take my operator. I can compute here these integrals. I sum these integrals. I divide by j, obtain this number. You know, you can put this. You can program Mathematicas and you have this number without any problem, and then you have just to compute this kind of limit.
Yeah, I'm asking because usually if you are speaking about a Dixmere trace, then there is some integration in the sense of the Wojcicki residue, okay, on the cosphere, unique cosphere bundle of the cotangent bundle. So this integration has nothing to do with this integration.
Has to do because this is hidden again. Here you have the structure of dictionary trace. In some sense, it's hidden. But what I will point out that here you have really a very concrete expression to compute.
I'm looking for the motivation of the title of this page, trace and integration. So where is this integration?
No, this is trace. No, this is
The only integration I see is the L2 norm.
this is, you know, this is this trace, for the trace per unit volume is a trace on my algebra, a trace on the algebra integrals. And indeed, you can interpret this guy as non-commutative. Even this can be expressed in the philosophy as a non-commutative integral with respect to this wage, which give you a sort of an infinitesimal volume, non-commutative space. Because of that, this is the part of traced integration.
Okay.
And then I'm just give you some formula which are related to this formula.
Okay, so it's a philosophical integration.
It's philosophical integration. Okay, now geometry. Topology. Right, differential geometry, differential topology to be more precise. To do that, I need a freedom module. I have my Dirac operator, I can compute my Dirac phase. Then I have this tripole, my representation, my Hilbert space, my Dirac phase. I can construct the differential. Okay, the first result goes more or less in what in the Jean paper is called the first Coulomb formula. Again, we can compute the trace current volume of gradient A, gradient B. Okay, when I a BR operator in the pre-sister algebra of this function, which are Schwarz-Dekine coefficient. This is a pre-sister algebra is very stable with respect to this type of differentiation. Again, we can reconstruct this quantity with a Dixmere trace of the differential associated to the operator A and B in the representation space. Okay. There is a key point here to understand a bit the result that I will give you in the next slide. When I take an element on this pre-sister algebra, and when I construct the differential with this Dirac phase, what it happened that these guys are in this space that I called S2 plus. Essentially, you can understand this space, and I'm saying this in some imprecise way, but just to understand, if I take two elements here and multiply this with the element, I'm in S1 plus, which is the ideal in which the Dixmuir trace is defined. Okay, then each time that I multiply two differential of this form, I'm exactly in a good place to compute the Dixmuir trace. And there is a second important fact that when I compute, usually one is in usual construction of a Freedom module, F has the property that square of F is the identity. Here, F square is not the identity, but when I compute the commutator of F square with any element of my pre-sister algebra, I obtain a compact operator. And the compact operator are good in the sense that are just in the kernel of the Dixmuir trace. When I compute the Dixmuir trace, it's not compact, this is trace class operator. This is trace class operator. When I compute the Dixmuir trace of trace class operator, I wish it, I trace it.
So this Gothic S refers to
class. I found this in a book by Traylor. And I like it. And the plus are just the Chapin class in the Dixmuir sense. Okay, the plus in some sense is the Macaulay ideals.
And 0?
0 because it's the kernel of the Dixmuir trace. Are the operator which admit the Dixmuir trace, which is 0.
So your magnetic spectral triple will use Chapin classes.
Sorry.
So you are using these Chapin classes in places which remind me the places where some compacts or some other things are used in spectral triple theory.
No, I'm just saying that. Well, clearly, to be in some of this class, this differential should be compact, but this differential is the action of this phase, which is a compact operator here with an element of the algebra, and of course, transformation but is more than compact in this Macaulay class. And the compactness indeed comes from the fact that the result of my Dirac operator is compact plus computation. So I'm not saying that is an immediate result. You have to make some computation.
So I wonder what is about this commutator with F squared?
I'm saying that usually when you construct a Freedom module, usually one of the conditions that is F squared is 1.
Yes.
In my case, it's not 1.
Yeah, so this is a replacement for this condition. And
I'm saying, well, I will see you that the fact that it's not 1, but it's just something that is washed away by the Dixmuir trace, allow me to compute the topology. The error is not important because just is cancelled when I integrate. Okay, this is more or less the importance of this remark. Now, as usual, I would like to construct my brother algebra, the RAM homology in some sense. I define the 0 cochain as the representation of my star algebra plus the identity. The n cochain as just the 0 guys plus n differential. And I have this graph, the usual graph structure. And now I want to extend the action of the differential on this complex. And this is done in this way, okay? Usual formula, I'm inventing nothing here. This is really the usual way in which you define the RAM complex. But now happens something a bit different with being the usual case. I have errors. Reminder, D is sending omega n to omega n plus 1 plus a terms which is traceless. And when I compute the d square is not 0, but is sending me something in the traceless.
I have a question. What dB does to S1? Is S1 a differential idea or something like this? What the dB does to S1 if you have S1 in omega NB?
You mean this S1?
Or yes, this S1.
Yeah.
I don't know because S1 by itself is not in my algebra. You know, dB. dB.
So I'm asking if this is an idea, because it would be then it would be natural to take the quotient modulo S1. Or maybe it's too naive.
No, you're okay. You can now, if you take the quotient by this S1, you obtain again, you obtain a true differential extraction. I don't want to do
I don't want a differential idea. Okay.
I don't want to do the quotient just because I don't want to. But what I'm saying, look, what I'm saying is starting from this line, that if you quotient everything for this idea of trace class operator, everything works as usual.
Okay.
Okay. But you have to remember something that this S1 is indeed in the kernel of the Dixnier trace. Then because of that, I don't really need to quotient for this reason. Let me write everything here. Look, let me define this trace gamma. Okay, this trace gamma is just the Dixnier trace times this operator gamma. This operator gamma, as a rule, for the moment is not important, but is essentially to compute the Dixnier trace. Okay. The first important remark is that all the omega kb, when k is bigger or equal to, are in the kernel of my Dixnier trace. S1 is again in the kernel of the Dixnier trace. Well, this gamma is just given, just obtained using only the first two Clifford matrices. Is not an exact grading of my Dirac operator. This is just common. But now, what I want to do, I want to construct a cycle in the sense of the non-commutative geometry. I call this cycle quasi-cycle just because of this relation here are not exact. But when I compute with the trace, they exactly do the right things. My integral, which is the Dixnier trace, well, times this gamma, cancel automatically the error. Okay, then I have this type of.
Yes, but if you divide by this S1, you obtain a graded closed trace.
You can do
So yeah, so
You can.
otherwise it's something with.
You can do that, but because I'm integrating with an integral which erases automatically the error, what is relevant to me is to have these properties. And then this is a cycle of dimension 2. I call it quasi-cycle, but this is a cycle of dimension 2 in the every good sense of a cycle.
Yeah, so if you divide by S1, you obtain a cycle.
In the paper, I put it this way. In the paper, I quotient by S.
Forget about quasi.
But okay, this is the main message. Okay, with this cycle, we do differential topology. I can construct the Chern character. There is another tau, which is now it's not the action and is not the trace. This is really these guys. Okay, this is a trilinear form. This is a trilinear map which goes from the SB times SB times D to C. And the class of this guy in the even homology is what is called the Chern. And now we can prove that we compute this formula over A1, A2, A3, we obtain the same type of cocycle in my initial algebra, which is the trace per unit volume of A0 delta A1, delta A2, partial A1, partial A2, where partial are the component of the gradient.
Can you remind us what this algebra is? This funny thing, E?
This algebra is the algebra generated by this jumping operator that I showed you. Linear combination with coefficient which decay fastly in the sense of Schwarz type sequence.
It's a magnetic Schwarz.
Magnetic Schwarz.
So it's not,
If you want, regular representation of element of the group sister algebra with a kernel which is a Schwarz function. Is another representation.
my question is about a completion. So my question is what kind of an algebra is it?
This is a pre-sister algebra in the sense that this is closed in the Frechet topology.
And it's closed under holomorphic.
That is closed, this is really a pre-sister algebra.
Okay. Mhm.
And then, if now I compute this, I have this character. If I pairing this character with a projection, I obtain really the Chern class of my magnetic projection. In some sense, all the non-commutative interpretation of the quantum Hall effect is recovered by this spectral type. But
You realize you have less than 9 minutes. Less than 9 minutes.
Well, I will say very few things and then you can stop whenever you want. I don't have to reach the end. I have now to admit another weakness of this result. I convince you that I'm able to do the non-commutative geometry in the continuum of the quantum Hall effect, but in my presentation there is no potential. I'm just speaking about pure magnetic operator. And I also tell you that if one wants to explain the quantum Hall effect in full generality, the potential and in particular the randomness is important. Then the next step is trying to extend all these results, including disorder.
So up to this point, you presented us some magnetic version of Kohn-Kubo formula.
In the continuous, without potential.
Okay.
Pure Landau Hamiltonian, no potential. Okay? Which is not realistic. No, it does not, is not enough to explain the quantum Hall effect in full generality. Because of that, the next step is to add the potential. The potential is introduced again. Here there is another mistake. In this case, this should be an R2 because I'm in a continuous.
But you spotted it as 4-1.
I'm collecting mistakes, but anyway, again, I have a space omega, P is an ergodic measure. Just to simplify my presentation, I'm assuming that the action of R2 over omega is transitive, in some sense that I have a single point, omega 0, the orbit of omega 0 under R2, not Z2, is the full orbit. Just simplification, that's not important. Now, what I can do, I have to represent my operator, my element of the sister algebra C omega in L2 over 2. I do the same game as before, okay? These are just multiplication operator. I fix omega 0 and I'm translating omega 0 with the R2 translation, again R2, and then I have nice multiplication operator. Indeed, this is a faithful representation of C omega on L2 over 2. Now, result. Let me construct element of this formula, my jumping operator with this multiplication operator. Okay, these are monomial. And let me construct a finite linear combination of these guys. Okay, the really finite linear combination of these guys. This is a linear space. Let me put in the topology of the bounded operator in F2. I was telling something that is a sister algebra, indeed is isomorphic to the cross product twisted by B. Okay, now in this representation, I'm in the left regular representation of my cross product, the element of this algebra can be expanded in this very simple operator. Okay? And this, I think it's interesting because this is a linear space. There is no reason because, the closing these give me a star algebra. Even the star operation is weird because if I compute the star of this is mg bar upsilon kj. And then I have to reconstruct this operator as upsilon jk mj, but indeed this happens. Okay? Again, this is another way to reconstruct what Jean called the non-commutative Brillouin. Well, let me go. This is the right algebra in which I can consider my operator with perturbation because of the resolvent formula. Then I can consider really the resolvent of the Landau-Hamiltonian, which is here in the magnetic operator time potentials, which are here. In some sense, this just justifies that now I'm finally in the algebra in which I can consider magnetic operator and potential.
So physically, what is this space omega?
I have 5 minutes. Can you ask me this at the end of the I would like just to present another result and then I stop. Again, as before, now we can construct the same type of LP space. Now I'm replacing another mistake. I don't need this HK. Okay, just remove HK here. I'm replacing the coefficient, the LP question coefficient on a sequence in C omega, which LP, when in the sense of the norm. Okay, this is an algebraic angular norm. I have this inclusion of this space, which looked like the inclusion before. Again, I can define a space which is given by multiplying 2 elements of the type LP. This space now is a bit smaller of the domain of the trace. Now, again, tau here is for a trace. Indeed, in this space, E tilde, I can compute a trace which is of this form. Any element is a product of 2 elements of this type, A1 and A2. And these are elements, remember, this is really the left regular representation of the cross product of a kernel. And the kernel of this guy, A1 and 2, of the type L2 of omega F2. I can compute in that this scalar product with respect to this L2. It turned out that, again, this trace is nothing more than incarnation of the trace per unit volume. Now I have also to remember that I have omega, and then in the trace per unit volume, there is the averaging with respect to this. I'm expressing this in this way. Well, on this ideal, we can prove again this type of result. We can prove that the trace per unit volume of my operator can be again re-expressed as the Dixie trace normalized by the inverse of the modulus of the Dirac operator. Now, again, on this space, we are not able to prove this formula for the full ideal, which the trace per unit volume is defined. But again, this is a huge space which contains the 3-star algebra of the Schwarz type operator. What we would like to do is to re-obtain also in this case the energy shell formula. We hope that this formula should work even in presence of disorder, but this is still something that we are trying to do.
But you have this third collaborator to do.
I hope that it could be strong enough.
Exactly.
This is the list of things that we are indeed not able to do. First of all, to extend this formula to the full ideal of the trace per unit volume, to construct the Fredholm module associated to this new C-star algebra. This is the pre-C-star algebra which contains also the disorder. We have to prove the Kohn formulas, and what we would like to do at the end of this is to have an index formula of this type. I think that this is a correct moment to stop.
Okay, thank you so much. Okay, so the situation is reversed. Usually it's us who asks speakers questions, not the speaker who is asking us questions. So any answers to these questions?
Please.
Somebody wants to answer the open questions?
I have a question for the questioners. So the proof of the Conness formulas, that would be for the case with potential, right?
Yeah.
Okay.
So now let me ask my question. What is with omega?
I can give you a very physical construction.
Okay.
Take in your RD
Uh-huh.
a potential. Okay? Usually a function L infinity.
Okay.
Now, there is no reason to decide that the origin of your system is the most important physical origin. In some sense, your physics should be invariant under translation. Then start to translate your potential V with respect to all the translation.
In RD.
Okay, now, you know, these L infinity function are the dual of L1, then you can, in some sense, close this trajectory in the topology of the dual of the L1, obtain a compact space. In any point of this compact space is just your potential from the point of view of a different origin. Okay, any point omega is deciding from which origin you are looking to your potential. Essentially, this omega is considering all the possibilities of the realization of your potential, making it covariant with respect to translation.
An
It's like
example.
all possible choices of gauge.
No, in this case, it's just pure potential. It's the electrostatic potential. Yeah.
But let's take D equal 1 and give me some trivial potential. So what would be then omega?
Look, I give you an example which is a bit better.
Okay.
Take your potential periodic with period 1.
Okay.
Okay? Then your omega is S1, is the circle. Because, you know, if you translate of one period, you go back to the original configuration.
So
But you can,
It's like a fundamental domain of a periodic function.
but your potential should not be periodic because of that. If it were only periodic, we are in the periodic case, we can also consider random potential. Then if you random, you have also to accept that when you translate, you have different random potential. Then in some sense, omega is giving you, is parameterizing all the possible configuration of the disorder which are compatible with the model that you choose.
And the conceptual reason why it is compact Hausdorff?
Because if it is compact Hausdorff, in this topology, you have a nice result about the existence of measure. These are not only space, they are dynamical system because you have the action of translation.
No, I know what you need, why you need compact Hausdorff, but I'm
At least the
curious
polish.
why you get it.
Why? The reason,
You told me the construction which I don't really follow, and at least I would like to understand conceptually why this construction ensures that you end up in a compact Hausdorff domain.
I'm not saying that every type of potential give you can construct pathological potential that will give you this compact Hausdorff.
Ah, okay.
So could you remind us
Okay.
the condition for the potential? What should be the potential such that omega is compact?
This seems like being almost periodic.
An infinity with something else. I don't remember exact condition. Probably Jean can give it the correct, precise answer.
I think it's gone.
It's done. Okay.
And sorry, exactly related to that, it sounds like it's has something to do with being almost periodic.
No, almost periodic, give an example, but not necessary. Could be even more general than almost periodic.
Okay.
Or general.
But it's an example. In this case, you know, you end with the Born compactification over D.
So we have a stronger condition, which is this quadratic, and the weaker condition, which is L infinity, and this is somewhere in between.
This is a way to say that. Another way in which you can construct this whole, this is, I think, the first way in which Jean did. Take your Hamiltonian with your Landau Hamiltonian plus a potential. And then you construct the resolvent of your operator, translate your resolvent with respect to translation in L2/2, and close the orbit in the strong topology. Under very mild condition in the potential, which should be L infinity plus something else. I don't remember exactly which is the extra condition. You can prove that this orbit is compact. And Jean called this type of operator homogeneous. The closure of the
So
orbit.
this orbit is dense in something.
No,
Just
not the
compact
orbit.
house.
The orbit, you have a resolvent, you are translating this resolvent with respect to all the translation, and you close with respect to the strong topology. I'm giving you a realization as operator. I'm in L2/2. I have my Landau Hamiltonian plus D. I constructed the resolvent of my operator. Translate this guy and close this orbit in the strong topology of L2/2. This gives me a closed space which, under certain condition for the potential, turn out to be how is this?
I have a question as well. So the fact that we choose a family of operators indexed by these omega. So the interpretation you just gave a moment ago suggests like that it represents like the inaccuracy of our knowledge of the potential of the system, like the fact that we are indexing by omega. So it's not necessarily that the potential is random or something like that. It's just that we do not know it very well. Is that interpretation correct?
I'm just saying that when you have a physical theory, a priori, you don't need to decide that the place in which you are is the best place in the world.
Okay.
The physics should be, or at least this thermodynamics effect should be independent of translation of your system. The fixing it, is arbitrary.
Okay, so in principle, it has nothing to do with randomness.
No, it's also related to random, because once you have a random potential, again, you have a random potential, which means that in the space we have some probability distribution. But again, if you translate this random potential, it's still a random potential.
Of course, yes. Okay, thank you.
Anybody else from the room?
I have a question. So it is without this potential, you had this cocycle. What happens to this cocycle when you introduce this potential?
Something that we have to look.
What?
Is in this open question. No, in some sense, all these parts
Somewhere in this.
No, in some sense, what I mean, all the construction of the Fredon module, the construction of the RAM complex, and the study of the differential and of the cycle, something that we have.
No. I'm asking about this co-cycle. I'm not talking about this cycle coming from this Fredon module. I'm asking about this co-cycle. When you were talking about this twisted.
No, it's the same. It's totally
the same. Okay.
So twisting is totally, sorry. Do you mean the group cocycle?
So the scalar potential doesn't affect this cocycle. the structure of this twisted
No,
cross product algebra. Okay. Mhm.
this is really the electrostatic part of the theory. This is just
Yeah. So
Hamiltonian plus electrostatic potential.
So this is the case when this scalar potential is independent of time. It's independent of time. Yeah. It doesn't affect the magnetic field. It introduces only these electrostatics depending on these impurities of this material.
Oh, your electron is in a crystal, you know, the quantum Mole effect is usually inside a metal.
Yeah,
you have to take account of.
If you're in a crystal, this is not impurity.
No, but you're in a crystal and
But you can have potentials
first of all, you have to,
in account also impurities. So
yes, you have to take account of the presence of the nuclei of the crystal, which are interacting
And some
with the
defects.
electron, and some defects.
yes.
Everything are in this scalar potential.
So this magnetic nature of all your constructions is separated from this electrostatic aspects in a sense.
It is separated and is mixed only on the structure that I show you in some sense.
The only difference is that in this magnetic, purely magnetic situation, you have something with constant coefficients.
Yeah,
In a sense.
and now the coefficients should belong to the
So now your coefficients are replaced by this multiplication.
by the function on the configuration.
Yes.
Exactly.
So some very coarse topological properties of this omega and so could be proven even if you have the situation with not necessarily constant coefficients. Because you said that under some assumptions about this potential, it's the omega still is compact Half-Life.
Yes, and
So this electrostatics doesn't affect this topology at least too much.
no, it does not affect too much the topic.
Yeah.
Indeed, indeed, K theory. is still the same.
This, yeah.
Or is not changed too much by this. If this omega coefficient is contractible, like in several models, then the K theory is
Mhm.
clearly a situation in which this omega can affect the K theory, but it's something that is easy controllable.
So this electrostatic potential only affects these analytic properties of this algebra, but not
Up to now, what
logical invariants.
well, but you know, there is still to say yes is in this way. Should
At least your intention is to prove theorems in this direction.
Exactly.
Okay. What about this correct definition of the index? What definition
something that is
you expect?
You know, there is a third incarnation of the
You said something like equivariant index, but classical or
No, let me say,
please let me finish my question. Usually in this equivariant index takes values in the K theory of the group ring of the symmetry, something like that. Okay, or sister out
it's something that
of a group.
well, being an open question,
It's not a number.
I intentionally I decide to be not more precise, but let me answer. In the one of the incarnation quantum Mole effect that you can compute these Chern numbers, this is a Chern number in some sense.
Yes.
Can be computed like a Fredholm index of a pair of projection. This is the main result by Saylor, Simon.
Yes. But
Now, the question is, and again, this result, we can do this with this spectral type. We can associate to this certain character an index in terms of some Fredholm index given by the projection P, which is the projection that it's relevant, and the Fredholm, the Dirac phase associated with my Dirac operator. Okay.
Yes, I agree. But maybe I misheard. But I had the impression that you said something about the equivariant index.
Thomas, I think that this capital gamma is just some sort, it's not a grading, but it is not a group. So this index is probably not an equivariant index.
No, it's not an equivariant. This gamma is just a grading, a quasi
So it
grading
is
of
just an
my
ordinary number, yes?
Yes, this should be a number.
Yeah, so
A number which depends on the projection P, on the phase, Dirac phase F, and on this gamma, which is an half grading of my phase, because this gamma enters in the computation of my channel character. Which this index is, I have no idea, and I don't know if it exists. This is what I would like to prove. This is a question mark. This is here, but it should be. It exists a Fredholm type index that reconstruct this number just.
I get it. Yes.
So Thomas, you were alluding to the situation where there is some group acting, your operator is equivariant, and then its index takes values not in Z, but in the group ring, the K theory of group ring, something like that, yes?
In the representation ring, yes.
Yeah, in the representation ring of, yeah.
Yes.
Mhm. So here is not the case.
No,
Yes.
it's not the case.
Mhm.
Okay, any other questions from the Zoom? Ludwig, Andrzej, Ralph? Speak now or be forever. Okay, since there are no other questions, neither from Zoom nor from the room, let us thank our speaker again for his magnetizing talk. Stop recording.